The red planet beckons us toward it, and the day draws closer when humans will walk on its dusty surface, and the moons of Mars may be our gateway to that future. Today we are taking a look at the two Martian moons, Phobos and Deimos, named after the horses that drew the God of War's chariot, and as we'll see, they could potentially play a critical role in transport to and from Mars, in keeping with their mythological namesakes. Probably the two biggest differences between Mars and the Moon, for the purposes of visiting and exploring them, are how long it takes to get there and how much harder it is to get back off it. The Moon is more than an order of magnitude further away from Earth than any place on Earth is from another, but Mars is two more beyond that, moving from 250,000 miles away to more like 100. Neither has much gravity compared to Earth, but Mars has more. It also has a scanty atmosphere, just enough to make landing there cheaper in fuel than on an airless place, and also a bit of a pain to get off of. This is our core issue today because Mars is so far from Earth that any mission sent there is out of luck for resupply and needs to hang out there for many months, not days like the Moon missions. But so long as a mission has access to power and water, it can basically keep going indefinitely, especially if it has a lot of redundancy of low-weight objects like medicines, tools, or seeds. Power is probably obvious, but water a bit less so, and it's half our reason today for looking at the two tiny Martian moons, Phobos and Deimos. Water is very easy to turn into breathable oxygen and fuel, oxidizer, and propellant for a rocket home. Using the example of the Perseverance rover we sent to Mars, getting that 1-ton rover to the ground on Mars from the launch pad here on Earth took an Atlas rocket bulking in at around 500 tons, and if you wanted to bring that home, would have required launching it with return fuel and an initial mass of a lot more than 500 tons, especially if you were using a single ship. We have no desire to be carrying the fuel for returning to Earth, not just to Mars, but down to the ground and back up again. Instead, the ideas are to make fuel down on Mars and leave your return fuel to Earth up in orbit, along with any parts of your spaceship that you need for the voyage, but not for going to and from orbit. You can absolutely make fuel down on Mars. Electrolyzing water into hydrogen and oxygen is a simple and scalable process, and you can see the mountains of ice on the Martian poles, but the problem is we don't really want to do missions there, and we are not going to be able to travel much beyond the landing sites on early missions, especially without fuel. The good news is that we have good reason to believe there are subsurface ice deposits near the equator, and that is a wonderful thing because it takes a lot of fuel to get off of Mars. Its escape velocity is more than double the Moon's, and in practical terms, using our ideal rocket fuel of hydrogen and oxygen, a rocket getting off the Moon needs about 7.5 tons of fuel for every 10 tons of craft escaping the Moon's gravity, while one doing that for Mars needs more like 20 tons of fuel for every 10 tons lifted. And if you're planning on going home to Earth, most of that mass is going to be your fuel, so anything you make down on Mars is paying a toll of at least 2/3, practically speaking, probably more. Hence, if we can make fuel over at those moons, that's way better, because it means that we can still make fuel down on Mars, but a ship arriving from Earth only needs to carry the fuel to have gotten to Martian orbit, can retank to land from an orbital depot, and refuel on the ground to launch back to that depot, then refuel there for the trip home. Phobos and Deimos are both so pitifully tiny that we need not even consider their gravity. A person in a spacesuit could literally throw a fuel pod off Deimos, for instance. We often talk about generating fuel for Mars on the Moon, but even there you are spending about half your fuel to get it off the Moon, and then you have to chuck it over to Mars and burn more to slow it into orbit, though this is easier if we have a mass driver on the Moon. But while that's a lot easier to set up and maintain there than on Mars, it's still a big piece of infrastructure to be contemplating this early in space settlement. We also enjoy the advantage of proximity to our existing industry when we make fuel down on Earth, regardless of the percentage lost to get into orbit, as we have an overwhelming amount of infrastructure, industry, and manpower down here already. A base on Mars enjoys no such advantages over its own moons. So in our ideal scenario, a ship launches from cislunar space with the fuel needed to orbit Mars, picks up fuel for its landers in orbit there, lands on Mars, refuels there, launches back up, refuels again in orbit, and heads home. Or alternatively, we just build a base on one of those moons and interplanetary ships dock there and landers do too. This is handy if you're using an Aldrin cycler for your journey between planets, because the longest step of that is it looping out around past Mars, and you could just leave that ship on autopilot for that boring and routine journey and jump back on board when it came through if all the systems seem safely intact. In any event, one big caveat is that we don't know that Phobos or Deimos has any ice. They have virtually no gravity, so we can't take that for granted just because Mars does and our own moon does, and it's not too easy to check as what it would have would be under the surface. Phobos, being the bigger of the pair, would seem the better bet, but the big problem is that we might need a manned mission to set up such a facility, and we might find it had no ice available. Now, the good news is that you don't have to have water to make fuel. You can make it out of most things that have oxygen in them by pulling it out, which is true for most metal ores and rocks. And keeping iron or aluminum around as a fuel source is way easier than storing hydrogen too. Those specific versions, like powdered aluminum and liquid oxygen as a monopropellant gel, might be harder to store than others which might not perform as well, and is no easier to store that way than liquid oxygen and aluminum powder separately would be, so you might mix them shortly before use instead. Indeed, by preference, we use methane or ammonia as our way of storing hydrogen, simply because even though most of that mass is carbon or nitrogen instead of hydrogen in those cases, it's a lot more stable and easier to store without leaking, which matters when you want to make and store it for months or years at a time. What's more, whatever your fuel is, be it hydrogen or hydrogen bonded to carbon or nitrogen, most of your mass is actually the oxidizer. Burn hydrogen fuel and you end up with water, which is 89% oxygen by mass, compared to hydrogen, which is obviously 100% hydrogen by mass, though it needs heavier tanks to store it, or methane, which is 25% hydrogen by mass, or ammonia, which is 18% hydrogen by mass. Again, as opposed to water, 11% hydrogen by mass. So even if you're only producing your fuel down on Mars, you can save a lot by making your oxidizer up there. If the moons do not have readily available ice, you get your hydrogen down on Mars, either as hydrogen or as methane, probably as opposed to ammonia. Carbon is plentiful on Mars compared to nitrogen. On other bodies, nitrogen can be more common, and this is generally going to be a concept and process transferable elsewhere, like the asteroid belt, where water ice might turn out quite uncommon, but where you might be mining metals and refining them and using the oxygen left over from that to make up the bulk of your rocket weight going home, even if you decide it was cheaper to bring some fuel in from elsewhere. I am going to bet Phobos and Deimos do have ice though, but would not favor a manned mission there before we were confident on its occurrence and accessibility. The problem is that it generally makes more sense to pre-position lots of spare fuel and supplies in orbit of Mars before sending a manned mission there, and a robot can handle a rendezvous with either of those moons way better. You can slowly rendezvous over entire days with either moon if you wanted, and if the rocket doesn't work on the final burn, you're crashing at several miles per hour, not several miles per second. By default, you probably want to land on one of those lunar poles too. They're essentially in the sunlight all of the time, so while solar is weaker out there than here, it is essentially constant minus when it goes in the shadow of Mars, which it orbits 3 times a day, and the shadow is on order of minutes, not hours like Earth's night, or weeks like on the moon, so only very modest batteries are needed for operation there. Deimos is smaller and further out, orbiting about every 30 hours and would spend even less time in the shadow of the planet, but maybe further out than you'd really want your base. Both have their pros and cons, and I'd imagine both will eventually have their bases. I just tend to think we should pick one to have a base on it before we put one on Mars itself. The issue that gets raised a lot is that we wouldn't want to go all the way to Mars with some human crew and then not even land on it, and that's a fair point to raise, but I should note that we did that with the moon. Frank Borman, the commander of Apollo 8, who passed on not long before I drafted this episode, orbited the moon but never landed on it, as did 1 out of the 3 astronauts sent on the missions which did land on the moon. It is more attractive to imagine sending a ship that would park in orbit and send some folks down, but I'd rather see the supply built up in Martian orbit or on its moons first before we send a human millions of miles from help or resupply. And then from that disadvantaged position, have them try to get up and down from space to a planet too, which is even harder than the long flight between us and the red planet. I would make the case that we would be wise to consider either moon as a place to plant some equipment first. For one thing, those moons are free shielding from radiation and micrometeors. If you're planning to leave things in orbit for potentially months or years, waiting for ships to arrive with people, it's better to tuck them into some crater. Now the question becomes, can we clap together a reliable module that can land itself on that moon's pole, spread out some solar panels, and start crunching up rock to process into metal and oxygen, or drill down for ice, one that's able to produce at least a few times its own mass before breaking. To me, this experiment and prototype is honestly more valuable than rock samples off the red planet because it furthers space development, and developed space can more easily get resources landed on Mars and other places for settlement. If you got some simple module that can land on any rock or ice ball, spread its solar-powered wings and start pumping out fuel for a tank, I can now send unlimited robotic and human expeditions around the solar system and at decently faster speeds. It might be easier to run something like that on an RTG instead, a radioisotope thermal generator, but the big issue with solar power on Mars is the dust, and space does not have that problem, so I like it better there. Either way, while producing fuel here and rendezvousing for fuel does add another point of failure to missions, which is never a good thing, especially with robotic missions with lots of signal lag time, it is reducing your initial fuel burden by an order of magnitude. I also very much like the idea of having two places that can produce fuel on Mars, so if one of them goes bad, we have options. Fundamentally, I don't want anyone 100 million miles from home relying on a static fuel supply that's not several times what they need and stored in more than one spot. And such a device can be of fairly arbitrary size. I would guess one twice the weight of another would produce more than twice the fuel, so bigger might be better, but such devices might easily mass less than a human. Long term, it would be awesome if the device were able to make its own polished mirrors for condensing sunlight on its solar panels and cranking out airtight pods to put its fuel or oxidizer in, but that's icing on the cake, or Comet. So given my choice, I'd send these sorts of solar or nuclear fuel generators to both moons and two spots on Mars, and still send one with the ship and with the lander. That way the ship can meander over to Phobos after the lander deploys and make fuel while it waits or tanks up off one there, while enjoying lots of radiation shielding. But I also want a basic communication relay on anything in orbit, satellite, ship, or moon, so the ground team was never in comm blackout and still had a backup if the main one broke. Redundancy and backups are important. This message brought to you by Chief Miles O'Brien and the Department of Redundancy Department, which would like to remind you that redundancy and backups are important. This is an episode on settling both those moons though, not their initial use as fuel producers, but that is the big initial reason to put infrastructure on either, so it factors in the same way rum or tobacco did to settling the Caribbean or Virginia. Ultimately, these are both fairly tiny moons, so they are not eternal supplies of raw materials, not that anything is, but Deimos masses 1.5 trillion tons, and Phobos is about 7 times that. That's 10 and 70 times the mass of Mount Everest, and so it is hardly a trivial amount of mass you're going to exhaust. We are talking more mass than humanity has ever used in all our buildings and industrial forges combined, but Mars is 100 million times as massive as both combined, and at a certain point it gains sufficient infrastructure to offset the difficulty of pulling mass off it. Nonetheless, I think both could be thought of as the river deltas of Mars, that very valuable initial real estate that everything is going to move through. As an example, Phobos is a weird moon, very close as these things go and orbiting quicker than Mars rotates, so it rises in the west and sets in the east. A non-rotating skyhook hung down from Deimos could be just under 6,000 kilometers or 4,000 miles long, and dangle over the atmosphere at about 800 meters per second, or about 1,800 miles per hour, in comparison to the equatorial speed of Mars as it spins, 240 meters per second, or the low orbit speed around Mars, and in some ways would work better for spaceplanes to match up with than a fixed space elevator, which also would be harder to build. And I should emphasize that when I talk about Phobos or Deimos being small, Again, there's enough mass in Phobos alone to build millions of oil supertankers or aircraft carrier-sized vessels. When we get into that sort of scale, you take a bunch of those and run them off to the outer solar system to grab fuel instead. I am not a huge fan of geostationary space elevators, or since this is Mars, aerostationary, in favor of options like orbital rings and tethered rings, or some mass driver running up the side of Olympus Mons, but all of those options are way further down the line, and I just don't see building them unless you've either got very good automation of the clanking self-replicator variety or a few million folks living down on Mars, in which case these moons are great fuel depots and also great launch points. These sort of super strong tether tricks can also be used for catching ships coming in at higher speed to save rendezvous fuel for them or Mars and to launch them too. But while a big chunk of rock is not optimal for fuel production compared to an ice ball, it is very good for metal production and allows us to start making big orbital mirrors for warming up Mars, or big power collectors to begin beaming energy down to Mars where ground solar might not be optimal, or even creating a big L1 Lagrange point magnetic deflector for shielding the atmosphere we bring to Mars, like we discussed in our episode on making a magnetosphere for Mars. As we discussed a couple months back in our episode on statites and ligites, great big thin mirrors can hang basically anywhere in our solar system at an area density of about 3 grams per square meter thin tinfoil density, and can have lots of atypical orbits as ligites, even when an order of magnitude thicker or more. Thus, we don't need to get very delicate in our production of aluminum foil on Deimos or Phobos to start mass-producing orbital mirrors for Mars. Let's say we ended up with clunky satellites that had to average 100 grams per square meter, controls and all, to make for an orbital mirror around Mars, and one capable of providing its own station keeping by tilting those mirrors. You could still produce an equal amount of those to the entire surface area of Mars for 14 billion tons of metal, around 1,000th the mass of Deimos, the smaller moon, and actually less than a quarter of the current worldwide aluminum production here on Earth. Sounds weird, but you can build very thin and light in space, and yes, we could cover the whole planet, Earth I mean, in aluminum foil if we wanted to, without bankrupting the economy, ignoring the damage covering the planet in tin foil would do. Though it would save us from the alien brainwashing satellites. With those mirrors and shades and power collectors and magnetic deflectors in place, you could make Mars quite a nice place to live. More importantly, in the short term, you could be manufacturing a lot of the bulk items for strictly space usage, or deorbiting, like a drop pod for atmospheric entry, or the hull plating for Aldrin cyclers. And you could be making smaller mirrors massing on an order of magnitude of a few tons, that could focus on a usefully small spot and double the sunlight at a local base, and they might be thin and keep their shape by slowly spinning, or they might be collections of rigid hexagons strapped together. They might be dual-purpose solar reflectors and microwave power beamers too. I do not think you'd want to hang these at ground stationary orbit, as that's a long focus distance compared to lower orbits, but you could have a cloud of them orbiting and just switching which base they were flicking their light and power down to as they went, or even hanging over the poles to keep a constant beam on one place, as we discussed in that statite and ligite episode. What would Phobos or Deimos be like? Well, in many ways like any other asteroid we might mine. Early on, they have no gravity, so any human-operated facility probably needs a rotating habitat, probably something small on the order of a Von Braun wheel, and I think you would pick a crater to stick that in or even just dig it in. They are loose rubble piles with an escape velocity not much faster than a jog, so moving material is easy. Indeed, your big problem is losing material when you hit it, so you probably want to mesh or tarp over any sites you're mining. And one very easy method of transport would be just to use a fairly thin wire of a material of decent tensile strength, steel or carbon fiber would be sufficient, and just jam some tall spikes into the surface of either moon around its circumference to run a tram along so you stayed bound to the moon. Phobos, the larger of the two, is 26 kilometers or 16 miles across at its widest. Neither is particularly spherical in shape, and likely would eventually be reconstructed as something bigger and more hollow. Amusingly, there was a theory back in the mid-20th century that Phobos might be hollow, but those turned out to be errors and better measurements confirmed it had a higher density than they thought at the time. but that probably is its fate, to get hollowed out or expanded into a megastructure or a few of them. It's likely to have the resources to achieve that in too, as it is a very valuable rock. In theory, if we ever got artificial micro-black holes working, we might dump a black hole several hundred times its mass into its core, and that would replicate the Martian gravity below, or we could go double that and replicate Earth gravity, but that's obviously a very distant horizon sort of scenario. Albeit we might have that technology, if it is even possible, in a couple centuries, and long before any terraforming effort on Mars would have done more than barely gotten underway. Phobos and Deimos are very valuable rocks, and that's not actually that much mass, especially in hydrogen or helium, so if any place is likely to be able to afford such a luxury, I think it might be them. I'd be remiss if I didn't mention that Phobos is slowly losing altitude over Mars at a rate of about 2 centimeters or 1 inch a year. And we figure that if we left it to its own devices, it would either crash into Mars in about 50 million years or get ripped into a new planetary ring. It's a good deal bigger than the asteroid that hit Earth 66 million years ago and probably shuffled the dinosaurs off the evolutionary stage, so that's obviously something we would want to prevent. To be fair, using it as a skyhook platform does the exact opposite of that, but it's fairly minimal and there are other ways to slowly regenerate momentum, even if it is not a great candidate for electrodynamic tethering the way skyhooks and rotovators orbiting Earth and in its powerful magnetic field are. For comparison, I don't think either moon could ever be an equal to Mars, or even on the scale our own moon would be as part of a wider Earth region, but if we imagine Mars as the equivalent of Eurasia, Phobos and Deimos might be bigger players on their edge the way England or Japan are, but certainly would be on the same scale some of the better known Mediterranean islands are, or maybe the equivalent of Long Island in its relation to the US. They can be powerhouses in their own right, and critical pieces of emerging Martian civilizations. I would honestly not expect Mars to ever be a single nation any more than I'd expect Earth to be, but Phobos or Deimos probably would be, and since they are not that big, I could see countries back here butting heads over who got to use them, as they are a lot more strategically valuable than any other specific bits of Mars are, even well-known spots like Olympus Mons or the polar ice caps, since there's 2 of those and probably ice elsewhere underground. In that respect, while science fiction and futuristic speculation often likes to contemplate battles over the red planet that gets its name from the god of war, I think we see conflict or tension arising on those 2 moons a lot sooner and easier. That said, I think the future of the Martian moons is a pretty bright one, and in large part because they can first help fuel our explorations and settlement of Mars, and later perhaps very literally as they help forge the mirrors, collectors, and magnetic deflectors that will help bring sunlight to Mars and protect the seas and skies we might give it. When I was a kid, I always loved board games and puzzles, and one of my earliest futurist predictions from way back then was that we'd see more and more learning subjects get their own fascinating games, and one of the things I've most enjoyed about being a dad is getting to find games like those and play them with my own kids. It can be impressive what kids can learn if it's in a fun and well-designed format, and that's what most impressed me about Turing Tumble from Upper Story. Turing Tumble lets you build an actual Turing-complete computer that runs on marbles instead of electricity. It opens up the black box that is computing to most folks and lets you explore concepts like logic gates and processing or calculating in a hands-on fashion that you can do as a group, collaboratively, or solo. It is a real computer you build yourself and which runs on marbles. You can run any game or program on it if you had a big enough board and were patient enough, though you might need a board as big as Texas to play some newer video games. I was truly impressed how engaged my kids were with it, and I loved it too. It's just a fascinating and intuitive way to learn and hands-on experiment with the fundamentals of computing. It also comes with a wonderful graphic novel that gives you a story and presents you dozens of different challenges and switch diagrams to try before modifying and experimenting on your own. Upper Story's motto is endless curiosity. You've heard me talk about their game Spintronics before, and Turing Tumble is just as fun. Turing Tumble is named after the great Alan Turing, one of the fathers of computers, and a portion of every purchase goes to support the Turing Trust, which provides reused IT equipment loaded with educational resources and training to schools in sub-Saharan Africa. Learn more about the game and see it in action at upperstory.com/TuringTumble. Use the coupon code IsaacArthur for 10% off your total purchase. So that will wrap us up for today, but join us this Sunday, March 17th, St. Patrick's Day, for our Sci-Fi Sunday episode, Automated Justice, for a 50-minute deep dive on the role of AI in our courts and justice system. Then we'll return to the Fermi Paradox on March 21st to discuss that evolutionary jump from the simple to the complex, and if it might be the solution to the big question of where all the alien life is. Then we'll finish our discussion of last month on black holes by deep diving Kugelblitz black holes and using them for power generation, before finishing out the month with a bonus Sci-Fi Sunday episode on the 31st, Multi-Planetary Empires. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon. And if you'd like to donate or help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like Crystal Aliens at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.